All right, good morning, everyone, including the people online. So welcome to another session of this distinguished speaker series of the Center for Causal Discovery. It is a great pleasure for me to bring Dr. Jonas and Almieda to visit us and give the seminar regarding this. Dr. Almieda got his bachelor degree from the University of Lisbon, and also he got his PhD degree from the University of Nova of Lisbon. And since he's finished and his career has traversed quite a few places, so I will not go through all the places. At least there's quite a few years, 3 or 4 years, we were together at the Medical University of South Carolina. And the reason we put Jonas here is our center is really the center of the big data technology. And Jonas' research touches both sides of it. He touches the big data side, and he works with clinical data, genomic data, and also the different kinds of data. On the other side, on the knowledge side, he also has quite expertise. He spent quite a few years to work out the method of semantic web applications, and nowadays it's data common and all those things. So if you see the introduction from our announcement, you can see his work is touching all different kinds of fields. So that's really relevant to what we do. And another note is that Jonas is one of the most techie savvy persons I know. Knows all the current advanced technologies and try to use it. And he will try to preach to that JavaScript is the big language you use. So buckle up. Let's take a ride with you. All right, without issue.
Yeah. So thanks for the introduction and for the invitation to be here. It's a big pleasure to see old friends and make new ones. So I see there are quite a few students in the audience, and you can get my CV by clicking on my name here. You can get my slides by typing bit.ly, web pit, right at the top. And as the presentation goes, I would encourage you, especially if I'm starting to be boring or not making sense, just click on the link and see other slides, then interrupt me and ask questions. So I want to make this very interactive. Otherwise, I may go in the direction that you don't want. But for the students, I started as a plant biologist, so wherever you start your career doesn't always tell you where you'll end up. It's always a good thing to keep in mind. And one thing that is changing the way we do science these days is the way computer science, there's this joke, why is computer science called computer science? Not sure. No, biology is not called biological science or chemical science. Why is computer science called computer science? And so the joke is that because they want to be one. And they are becoming one. So we now see computer science joining the other sciences at the abstraction level, so creating constructs that help you think and actually shape or even constrain the way you think. So if you type bit.ly, web pit, so remember it's always going to be on top. If you go to the first slide and you click on my name, you get my CV. So many of the things I'll show, they are published, and I have the list of publications all the way on and on. So you can click on the links for anything I show that you will have a closer look. So the other thing I should say is that last night I was having dinner with Greg and Shingo, and I was complimenting them on this seminar series because I think it's a great idea to have this, what is it, Center for Casual Discovery. So I found out that it's causal discovery. So I'm going to invert the order of the slides and start by showing you how do we communicate causality to the domain experts by using the computer platform to let you do this. And then I'll step back and then we'll dive into the computer platform so you see how you can represent things. Because the fact, and someone was making this comment as well, the fact that you use, say, deep learning, because it's the cool thing to do. I spent most of my career in machine learning at school. It generalizes statistics at many, many levels from this, let's say, auto-associative neural network is really a type of non-linear PCA or multidimensional scaling, all the way to a universal classifier. But when you do all of these things, at the end you have a nice complex object with lots of matrices. And how do you communicate this back to the user? By claiming associations and ultimately claiming causality. So I won't be approaching the mathematical side of causality. It's the communication side where people can verify imputed causalities. So I'm going to start with something that is not in the plan, by getting a figure from a paper. Figure 4. Make it a little bigger. So this is the story. You're measuring a number of things from regular pathology and molecular pathology. And those of you interact with pathology hear these stories all the time. A typical or classical pathologist would say form is function. So we don't really need this molecular stuff. We can see the nuclei, we can see when they are divided. So this is from one of our projects at Stony Brook. It's U24, the page dual cells. I know quite a few of you know him. So you can get a tissue, and you can segment the nuclei, and you can choose the algorithm. We'll take a little bit, and then you see the segmentations. While it does this, on the other side, you have things like CBio, for instance, giving you the molecular data. Let's go back to the figure. So typical pathologists would say, well, if the nuclei are round, we don't have mitosis going. A molecular pathologist would say, but who cares? It's maybe TP53 mutation that has an effect. So by pulling data from multiple places, so now it comes the interaction that communicates the causality, you have this conversation between two domain experts represented in a shared platform. And there is something, let's call it magic, about having a shared computational platform where different knowledge models can interact with each other. So for instance, the typical pathologist would say, well, roundness, yes. So if the nuclei are round, the patient will live longer. So you just have a Kaplan-Meier model embedded in the application. And you can move this around to see how round is good. And the molecular pathologist would say, well, but if TP53 is mutated, that eventually is lost, and there is some small population that grows and eventually produces the tumor. So a lot of what I'll show you today is how to aggregate knowledge representations in interactive environments, such that different domain experts can engage your tools. I'm sure one day in the future we won't need humans, and so the machines will make interfaces for machines. I'm exaggerating, but until that day comes, the knowledge representation is something that has to include the human. So it has to be, it's part of the exercise. And a lot of my presentation is an excuse to talk about causality from the human-machine interaction side. Oh, we never got to get segmentation in real time. Okay, now back to the presentation. So from the title, this is a presentation that brings the topic of data science to some sort of clarity. The field is just beginning. It's common to hear people from, say, the statistics side saying, you know, we already have data scientists, they're called biostatisticians. And indeed, we have 150,000 biostatisticians in this country. We don't have 15,000 data scientists. Maybe we are now heading that way. So why is a biostatistician not a data scientist? Sure. What is new about this field? And I hope by the end of my presentation, you see that the transdisciplinary nature of data science is really what defines it. So I'm now quoting from NSF. NSF had a working group on this. What makes transdisciplinary sciences different from multidisciplinary sciences, which themselves, of course, are different from a science that has a thick vertical? And the answer, to get the philosophy out in the beginning of the presentation, is that in the transdisciplinary side, you're working around narratives. So you're trying to abstract narratives that cross multidisciplines. In the multidisciplinary, you're trying to be good at more than one field and be excellent at the interface. And of course, in a single discipline, you're trying to be as vertical as possible. So again, as I go to my presentation, this idea that, for instance, if you don't know how to program, you have a handicap. So there's a literacy in data science, which is the ability to engage the machine programmatically. But not just the machine. Data science starts with data for a reason. And since I have enough students in the audience, I feel compelled to give you an example of how bioinformatics became a discipline. So there was a field before called biomathematics. And they were known for doing things like modeling spherical clouds and infinity flatfish. If you Google this, you'll find there are books written about this idea that people would use physics paradigms to abstract biological constraints that did not match reality. And so at the time, you could say, okay, we can see how this happened a long time ago, in the 80s maybe, before we had sequencing and other things that required computer science to come into this conversation. So the first group that started working on bioinformatics was in French Quebec, and so it's a French word. And in no language but English, informatics means computer science. So bioinformatics, so it's a biology, so it's biological computer science. It came back to English as bioinformatics. So I'm telling you this story so we understand why data science is called data science. Because we've been spending so much time on algorithms that do not reach the place where they are consumed, that the people who are creating the need for a new field, they want to make sure we start with data. So the ability to interoperate with data sources is critical to data science. And I'll show you many examples where, for instance, we traverse 70 million patient records on the fly. So this ability to traverse data, to engage data, is very much what drives data science, unlike other fields. I'm not that mouthed by statisticians as Xinhua knows. I was one for 5 years, 10 years, and all those things. So I'll be that mouthy myself. It's just that the field is changing. Okay, so let's have a quick look. So as in all fields of academic inquiry, data science starts with an identity crisis. That's what we have now. And so let's get started with how this identity crisis is being addressed. I have a second abstract for the bioinformaticians. I suspect with Xinhua being here, that will be a nice cohort of bioinformaticians. So if you don't like the first description, use the second. I also leave here at the end a number of examples. Figure 4 is here. But I leave you a number of others. For instance, here's another one. So this one came out on a paper called Open Health. So as usual, if you go to the CV and you look for the keyword, you'll find the PubMed link. So this is an example where something is happening somewhere. The data is being streamed out somewhere, and we'll get to somewhere in a second. And I need to have a real-time interaction with the data. So you have here observed versus expected. And here you have different places in Suffolk County. So this is Long Island, you have Nassau here, you have Brooklyn, Queens, and then Manhattan, and goes on. And we'll go to maps where the other counties in New York show up as well. So let's say a patient in the hospital. The patient is the ultimate consumer of our science. It's important that we can reach consumers that are both researchers and will benefit from what we find. And there's also an element of policy. So we're now in a realm that goes from patients to hospitals, and things become complicated. And you know, the healthcare reform is pushing for not payment per procedure, but payment for performance. That's a trend we are heading to. So the ability to be green is great. So if you're green, you're going to be rewarded for treating the patients better than the models thought you would. If you're red, there's a problem. And there's a conversation going on, and again, this I think speaks a lot to causality for what and by what, explains why data science is very much part of your narrative. So you see that, so I'm going to cite 2009, that the different counties go up and down, and you can stop and pick the bad guys. For instance, here you just pick the bad ones, find out where they are. You can maybe tabulate them, engage them, so that they are all in real time. So you see things going back and forth, so let's do it once more. So I don't confuse you, so not stop and talk. It is, see, up and down, up and down. So the observed value changes a little bit, and the expected value does not. This is what you'd expect. Populations don't change from one year to the other. Some people leave, some people come, but it's a small change. What changes is environmental factors that, let's say, for instance, there's a flu epidemic that will change COPD, or there's opioid addiction now is a big problem, as you know. It's apparently more harmful than HIV ever was. And so we see these effects going up and down until you get to 2014, where everything moves sideways. So the state, without telling us anything, start playing with the models, the predictive models, and they change the goalposts. So the goalpost is what you expected the disease to have incidence in a specific area, in a specific zip code, taking into account the demography and other clinical information, a bunch of other things they have in their multi-logistic regression models. And then in 2014, they decided to change the goalpost to see how it would look like. And then they decided it was not a good idea. Everybody would be red. It makes no sense. You know, there should be some zero at the median. And they went back to the old one. The point I'm trying to make here is that this idea of engaging live data, where the data is a point made years ago by Alex Zali in a famous paper in Science called Beyond the Data Deluge. If we don't have a direct connection to the data that informs models, the models will often be misleading. So had we been paying attention to what we get from the Department of Health of the state of New York. We will never get a memo saying, hold on guys, we are going to mess things up in 2014 and then we'll go back to normal just to see what the payments would be. So a lot of models only make sense and only come to our attention if your code goes straight to the data. So I see some puzzled faces. No? Okay. I did not convince you. Let's try something else. Okay. So you have an EMR at your hospital here. And so do we. And we can use it. It's quite a bit of work, but we can use it. Should be quick. So you can, if you're authorized, you can get the apps and find out, for instance, nosocomial infections at Stony Brook. Here. And I'll just show it very briefly because this is clinically derived data. There it is. It's gone. But see, I had to hide it. And you as researcher says, well, we're not physicians, but we need to investigate the phenotypes of human beings, not phenotypes of mice and cell lines. I mean, of course, we need animal models and cell lines. But a lot of the things we are going after, from genomics all the way to clinical and epidemiology, are things that involve humans. So we need patient-derived data. And of course, you'd say, well, we have the cancer genome atlas. We'll get there. That's where I started my data science career, was in the GDAC in the Kennedy Anderson Cancer Center. And the problem was, in fact, to get the data. At the time, it was in the days of CCD. Some of you have nightmares still about CCD. So how to get the data, how to download it, how to understand it. And the data was constantly changing. And this will be a topic of today. How do we handle data that changes constantly? As our knowledge models change, so do the representation of the data. So this is an example of how the problem can be solved. The Department of Health, the state of New York again, it's a department we are very thankful for a number of reasons. They divided their data streams into parts. So we have trouble getting to the hospital in a way we can publish. And if we can't publish, we can be rewarded for the value we provide to patient care, but we can't really behave as scientists, and that cuts us loose. The Department of Health separated the data streams in two groups. One group still, all the billing information, they go straight to the academic under HIPAA cloud, where things can't really live except in aggregated form. And they also experimented the other side. Let's make the patient data available at the individual patient level. So I have here an example where I just traversed, so I'm going to do it again so you can see it. I encourage you to do it in your cell phones or computers. So you just have to type deeply, and type it once more, deeply. Load Sparks. Is the font too small, or you can see it well? It's okay. Back in my sleeves, I just traversed, let's count them, 17,563,754 patients. So the patients are now segregated by a number of parameters. Let's just pick one of them. Let's see this one. And now I'm pushing to the environment that many users are familiar with, which is an Excel spreadsheet. No surprises there. But now we could go further. And for this data, you have very granular data. You know where the patient is. Let's go back to the other line. Again, I see some puzzle faces, so I'll go slowly. So I'm going to copy the link. And I'm opening it in a new tab. So really, really gently. And instead of asking for comma separated values, which your computer will immediately try to represent as a spreadsheet, I'm going to use something we like better, like JSON. And now you have the patient record. I'll let you look, because it's really impressive how much you know. This is someone that's alcohol and drug dependence, it's heavy stuff. So it's a male, non-Hispanic. This is the zip code it comes from, only the first 3 digits, but goes all the way to what is the operating certificate number. So who treated this person? What was the cost? The license number here. Physicians have no HIPAA protection on the patients. It goes on and on and on. So you can guess that there's a lot you can do with this data. This is resolved at individual level. And it's also worth noting that you have some beans with only a single patient. So the idea of patient confidentiality is a conversation that we have been avoiding by using HIPAA as an excuse, but we're just not talking about it. So patient confidentiality ends the moment you know something about a patient. You know the gender of the patient, you know which half of the population. But this means that a lot more data in data science is coming our way in healthcare as they do in other things, in shopping, in politics, and so on, that describes our population with a lot of granularity that we need to engage as researchers. We've been treating this sort of data, this social media data, as something that does not belong in healthcare, but it really does. And this is an example where the same mechanisms, the same APIs are making this data relevant to us. So now, for instance, you could look for cancer. And you could just look at who is treating who in Suffolk County for cancer. Let's click on it again. You can export it to your environment of choice, R, MATLAB, Python, wherever you want. Just click here. All this goes through the cloud. And so my question to you is that, is this more compelling than the other one? We are looking not at zip codes in Long Island, but the whole 17 million patients. I didn't download or install anything, and I'm traversing large amounts of data. I'm doing statistics on them. I'm doing Kaplan-Meier estimation. So all these good things. And I never left my machine. So what is going on? Let's continue a little further. So what is the command line of this computer we are working with? And you saw in the abstract, I started by saying something that a few years ago would not be as recognized. I started by saying that the web became a global data space. So this is computer science lingo. And now we find this acceptable. A few years ago, we didn't. For instance, MD Anderson, at one point in the beginning of the TCGA project, was spending $2 million a year to keep a local copy of TCGA. I lost track of the size. The last time I heard it was 2.5 petabytes. I'm not sure, something like that. And so it does not make sense for the data to exist in more than one place. And the people that found this first were not biologists, were astronomers. So that's the paper I mentioned it, Alex Zale. So the idea is if they have more data than we do, so this image is taken every so often with the night sky, and they couldn't possibly move the data to the place where it is analyzed. So this idea that the code has to go to where the data is unavoidable in the case of astronomy for logistic reasons. In the case of health, for governance reasons. I can see bins of one patient, but I cannot abuse my ability to find out that this is my neighbor. So I have to find a way to write my algorithms in a way that the code migrates to where the data is after inserting itself into the governance space of the user. So again, some puzzle faces. Every time you were puzzled, I have to show you something. So I'm going to try to talk to my Fitbit. So that's a personal relationship between me and my Fitbit. It's none of your business, right? So let's get started. Connect to Fitbit. I should show you the URL. So let's go back. So I do this slowly, and you see why big data in the health life sciences domain involving patients require you to use Alex Zale approach of pushing the code to where the data is, not because the data is big, although that may be a reason, but because the data is governed with some constraints. So here I'm at Stony Brook, SBU BMI, so Stony Brook University, Biomedical Informatics. I wrote the code. And all these issues of attribution should not be challenged by you. Says, you sure you wrote the code? Maybe you had a student write the code. Yes, see, I wrote the code. See my picture. And you can see every version of the code. So this idea that now we talk a lot about the fairness in the work we do, that everything has to be findable, interoperable, reproducible, etc. The attribution part is fully guaranteed in this sort of environment. So we have to be working in a way that the code can be interrogated all the way to the bit, but the data cannot. So that's the point. The data is private, the code is silent, it's public. So back here. So I'm at Stony Brook University BMI. This is GitHub. I'm serving it directly from GitHub, which I imagine all of you use. Right? And so the next step is I go to the company that manufactured the device I paid $150 for. So this is my relationship with these companies. None of the hospital businesses at this point. And I'm using OAuth. These are names that are going to become familiar to you in the coming years if they're not already. So that's the abstraction that deals with governance in the web computer. We're talking about web computer. And when I registered my application, I declared where it comes from, and I'm engaging the scope set by whoever I have a relationship with. So if you picture yourself as a human being, we are studying phenotypes. Human beings are the last large cohort of wild animals we can study in detail. Maybe it's a good image because how we treat wild animals when we study them, we put collars. So they did. I'm a wild animal with a collar. But I have rights that these other wild animals with mistreated do not, and so these rights have to be protected. So my code has to go to this protection zone. So whoever sold me the device, I signed the contract, all these things you sign all the time in Google Trade, saying that they would scope the permission to my data by sleep, profile, friends, and so on. And I says, well, I don't want you to know where I have been. You can have my activity, my heart rate is fine, not the food, not the weight, not the devices, not the friends, you can have the profile, not the sleep. So the consent process that typically you, as a patient, you do at the hospital is already being automated when you are a consumer. And people before they are patients, they are consumers. And there is a continuum between the fitness domain and the health domain. So what we are now entering is an era where we can engage, we can do preventive medicine by engaging people before they are sick. So the hospital is now extending it outside. If you go to EMR websites, you find out this category is called this consumerism in healthcare, and they're selling products. So we engage patients before they are patients. So when you have a tummy ache, you have your phone and it texts. It says, I have a tummy ache. And this goes somewhere, and the interaction already started, so they know who you are and where you should go. So I just went through the consent process without using a single piece of paper. And data, so now I have my data, and I went back to Stony Brook. So if you look at URL, I'm back to the same place. So this is the point in time we are in the data, excuse me, in the data sciences. We are all able to read anything that is consented. From genomics data, we remember the 500,000 23andMe records that Stephen Frank analyzed. It's a fantastic paper about resiliency in human genomes, why some people are healthy where they should not even be alive. You need to comb a lot of data to find this sort of information. So same thing here. So anyone wearing the Fitbit just has to find a reason to click on my link and for the data to become available for your mathematical models, for your causal models to be used. The point in time we are is that at this point, we don't have any place to put the data. And you notice in the abstract, I put a little emphasis on fire, HL7 fire. And I think everybody heard about smart apps. So the planet of the apps is now starting to have some smartness on it. So the smart layer is the same OAuth you just saw. It's a little bit more complex, the scoping in healthcare, as you can imagine. If anyone is curious, I'm happy to show you the resources. You will scope in a smart app when you get sick and the hospital invites you to have one with you. So you just saw the process all the way to me having the data in the application. It's ready for my mathematics, but I don't have any place to put it. Any questions? Sure you do. I have a Dropbox account. Yes, we could do that. But you go ahead.
You have a million record example. How do you do it? Is that all server side?
It's a very good question because we have a million patient record. All of us heading our way. It's exactly a million. And the question you're asking is the one that is debated now. So now I'm putting my boundary condition hat as a researcher. We should explore the answers to your question in boundary conditions, right? We know the final solution is going to be somewhere in here. So in one boundary condition, it says you're thinking, well, does the patient have a place to put the data? You could say, well, Dropbox. Not everybody has Dropbox. But maybe everybody has Facebook, or they have Google. So all of these social networking cloud-based systems, they expose their APIs for us to write back to. So in fact, we can write back to their, let's call it root sec, to their social computing root sec, and then turn the healthcare, the personalized medicine exercise, an exercise of engaging them in the social computing side. On the other extreme, you have the OMAP group, with these people that have standardized representation of clinical phenotypes, such that people from the comfort of, say, R or MATLAB or Python, they can engage these abstractions and they can basically be trusted with a lot of data. So I'll leave it up to you to decide which of the two is going to work. I also think it depends a lot on healthcare systems. We are not the only ones doing this. The whole world is doing this. In some places, things are too rigid to do anything but the OMOP approach. In other places, it's going to be complete market-driven, so it's consumer-driven. And there is a book I highly recommend in this context, which is Eric Toppel's The Patient Will See You Now. Not sure if you heard. So he's the director of the Scripps Institute. And he's advocating that the patient as a consumer will drive the process up to the point where it's so sick that it requires additional infrastructure. But the first part of the process is going to be driven by this patient who will see you now. So I defer to the book, the full answer. Now, I've been babbling for half an hour now, so I'm past the middle of my presentation, and it's time to startle you a little bit, I think. So let's go to any page. It's the University of Pittsburgh. So this is apparently a web page. It's where most of the human population lives today. It's in the web. We'd like to engage people who are in this domain. So let's open the console. So what I did is something you can do now. Some of you have computers. I'm going to do it slowly. Can do it really slowly by, I don't never do it this way, so I forget. So you go here at the end, more tools, developer tools. So compare this with this. So I'm starting at lab. You could do R if you prefer. It's all the same. So what's happening? I'm waiting. Meta is still coming. While it comes, I'm going to brag a little bit and do the same thing on my cell phone. Alright, it's coming. Fine. Okay. So we could do, for instance, something like this. So now we have to embed this. Yes, there it is. So what's the difference between this and this? So there are some differences. This one is faster, much faster. It has access, for instance, to GPUs, at no cost to you, the API is exposed. It's much better connected, knows who you are, and everybody has one that is truly theirs. So the things we've been doing in R, in MetaLab, in other environments, and I've been there. I started with Fortune 77 a long time ago. All these things are now available in the environment of the users, so of the patients, so the physicians. And there is no way, I've tried it at Jonas, and I'm happy to tell you this story. So we developed a tool called Nearest Related Neighbors that to run required the use of a full Cray machine. My Cray machine at the time had 80 batch nodes, and if I remember the numbers right, and I had that just for me. So I had runtime servers in each node, and I had this parallelized process going on. And then this had to be made available to the clinical side. So this is completely unsustainable. The code base is complicated. The runtime servers change over time. The paper I published at the time is now accessed mostly by people that want the version of the runtime machine I used at the time because they want to run old code, because the new code requires. So you see, it just does not make sense. The way we've been working until the data science boundary starts is not going to do well when we move to the next stage. And that's, in a sense, I'm making these predictions because they are cheap to make, but it is my understanding that what happens next with data science is very different from what happened before. It's a completely different way of storing data and handling, pushing computation to where the data is. There are some good news and some bad news. So people of my age have to refactor a lot of things they did. And the refactoring code, as you know, it's always complicated. Sometimes you can't publish it. I have an example here where I refactored something. So factor, decomposition, sequence analysis. But you can imagine the nightmare it's going to be to do this. So after I refactored the code, so factor may produce the composition sequence and alignment, I can start to deliver my code in ways that will live in other places. So I'm going to move now from PubMed to the University of Pittsburgh. So I'm going to run the same algorithms in both places. So here I advertise that I have a GitHub page. There it is. And there's some figures of the paper, like equation 2 and equation 3 and 5. You can try them. So I could type some sequence. Crazy, let's copy it a bit. And I encode it. And I write write some programs, that little piece, and you see the alignment data. If I copy those 10 on. But I could also open the console and do U equals to U SM, and then the sequence. It's where the sequence is. And you can say, fine. So you imported your code in a way that runs in the browser. So some things the browser is good at is the browsers increasingly don't stand on their own anymore. So if you're running something on the browser side, on the client side, that is computationally heavy, the libraries that mediate the access to the server side will automatically push the code to the server side. Some browsers are designed for this. For instance, the Amazon Silk browser, I'm not sure if any of you is the Kindle Fires. So when I write my code, it runs faster in my daughter's Kindle Fire than it does in any computer I have, because the JavaScript are like being computationally intensive. The compiler quickly realizes that I'm not going to run it here and sends it to the cloud. So the good news for us as scientists, not as programmers of MATLAB or R or Python or whatever you like, is that our mathematical side is going to be much better treated by this new world than it was in the past. So our code is going to be sustainable. We are not going to have services that stop working after 18 months, which is the half time for bioinformatics service according to a paper in nucleic acid research. 18 months. So publish the paper, you get a patent back, and you abandon your baby. This is what we do. We also publish lots of code, and I'm happy to share my own that no longer works. Right? You too? See, we'll do. So this doesn't make sense that we spend all this time coming up with algorithms, packaging them, making them available, and then they don't run after a few years. Makes no sense. So the other one is this idea that there are some abstractions, come from functional side, that are starting to be part of the toolbox we have in the browser. So I don't have enough time to show you a few more things. But let's do this one. So I'm going to create a matrix. And now I'm going to create a little function. I'm going to use old syntax. So I don't go outside. Start on one, but if anyone doesn't like the C Java syntax, I move to ECMA 6. So it's up to you. There's other syntaxes we can use. So also this idea of writing languages with multiple syntaxes, it's new. It's not part of our training. Our training is that if you're writing MATLAB, you have that nice indentation, so you're doing Python and Julia. But if you're using R, you have a little crazy stuff going on in the syntax side. If you're in Perl, you're lost, and so on. So there are different levels of cleanliness. But we are not used to seeing completely different syntaxes in the same language, which is what's happening in the browser. So if you don't like JavaScript, no problem. Use something else. As long as there's a transpiler that makes the conversion. So I'm using the Java syntax or C syntax. Anyone? We use this as a test when we hire programmers. 18. No?
XI when you're arguing, then you return 2 times X.
Very good. You're hired. Okay. So now if I do this, this is a vectorized operation. We all learned this in our languages. We get all of them multiplied. So this means that the opportunities for parallelization are now enabled to the compiler. When we are using our own machines with MATLAB, you're using something like R4, R as an equivalent thing, that you specifically say each loop is self-contained, so it's self-scoped, and then we're going to distribute this by a cluster. And it's you're fine, you can get your genomes assembled really, really fast. The other one is reduce, and our ability to handle NGS data is entirely based on this paradigm that we have a functional method where we can refactor our code like you saw for USM. So I refactored it, I spent some time to break the sequence alignment algorithms, the Newton, Wunsch, the Smith-Waterman things we learned a long time ago, but to free them from the constraints of dynamic programming. So a lot of the solutions we pursued in mathematics before, they were in fact, without our knowledge at the time, constrained by the imperative environment or object-oriented environment that we're using to code. We had this argument last night, Craig, so I'm abusing the podium because you can't reply, then I have the microphone. But my argument is that our computational literacy, like any type of literacy, changes the way we think. And so the way we do mathematics is it's less pure than we like to think. So for NGS, if we had to parallelize the assembly of the reads, it would be a nightmare, because we'd have to be excellent at many different things. But because we had already machines that were doing MapReduce, MapReduce was a Google invention, big table. That's what enabled a lot of the things that Google did at the time. They now moved.
Oh, I mean, MapReduce was 30 years old.
30 years old, yes.
Google. So it's not.
But
They popularized it.
They are better at marketing than the usual guys. So I still MapReduce. So I'm going to add two numbers. And also make a Google this time. A plus B. Okay. So S23. Anyone? So if I now go here and just say map reduce. So it is. So the interesting thing, and no MapReduce is a bit more elaboration, issuing keys and so on. But the main point is that I just declared two order-free operations. One of them is a typical vectorization, the embarrassing parallelization. So if you had many agents, each of them would go to an element of the array, they would consume it, and they would poop one. So eat one, poop one. In the reduce, I eat more than one, and I poop less than I ate. But that's it. So with these two simple abstractions, that like Mr. Pacman, you can imagine them, you can suddenly sit on a bench in a park and start thinking about algorithms that you will be able to scale on someone else's dime, on someone else's governance, on someone else's infrastructure at no cost to you. So this, for me, is what data science, for those of us who like algorithms, gives us as a present. Our ability to think and then produce things that are eternal, will live forever, and they are sustained by other people. But at this point, someone says, yeah, but JavaScript is going to change, right? No. JavaScript is an assembly language, and assembly languages are constrained by the market. So they'll never, the backward compatibility of JavaScript after a certain point, which is already in the past, so no danger for you guys, is guaranteed by the market of, I don't know, many billions of users. Now at this point again, so to make the language point, then we move back to the slides. What language runs in your browser, right? Everybody says, oh, it's JavaScript or something transpiled to JavaScript, like CoffeeScript, TypeScript, and so on. What about in the server side? It says, well, a lot of Java, for sure, right? C++, some Fortran still hanging out there. So there's this place where you can count the server-side modules. And, for me, it's always embarrassing for me when I mention a point in time to a student and says, but you're probably in high school then, right? And the student says, no, I was not born yet. So for someone like me, 4 or 5 years is a small amount of time. We have algorithms that take a decade to mature in our minds. So this is very little time. So this red line is what's called a headless browser. So the bulk of the server-side computing in 2017 is happening by browsers that don't have a UI. So when we are comparing the browser with MetaLab, and we're saying that this is the exact same thing, what we see is that in time, I have my emails. If you go to the past, we started by having a command line, and eventually, for instance, in the case of MATLAB, it's the one I'm more familiar with, because R came up in the middle, and there was SPSS and other things. But MATLAB is very clear. It started as a Fortran macro, then it moved to C, and eventually added Java to it. But what they did is that they transformed the backend, just like we see now in the cloud. So the cloud is changing. The assembly language is JavaScript, but lots of things are happening on top of this. So as time moved on, we went from having just a command line to having a UI. The web computing world did the exact reverse. First, you had a silly UI that just could click in things, and you had hypertext, nothing else. And then these very efficient compilers were added to it. These debugging environments, you can do all of your debugging. It's a full-fledged IDE. So when I created my slides, I did everything without leaving the browser, saving, writing, and saving, writing, and saving, which is the way the web was designed originally by Tim Berners-Lee. So the original browsers, experimental browsers, were browsers to read and write, not just to read from the web. So we have, basically it took time, everything takes time in science. It took time for the web to be consumer-facing in the form it was imagined in the 80s. So you now see that we are caught off guard in our classes. I had to change the way I teach around 2015 because students were very informed than I was, and they were challenging the way I was delivering what's now called microservices and doing Informatics. Okay, so now, since we don't have much time, I want to leave time for questions. I'm going to go quickly through the slides to see if there's anything important. Okay, this one is important. So this is the changes in architecture. Those of you in computer science always learn that the data layer and the application layer or the presentation layer, they have to be decoupled, such that those of us that produce data do not constrain the ways the data is used. Most discoveries in science are achieved by secondary analysis. So it's not by analyzing the data you generated, but it's by considering an hypothesis, potentially a causal hypothesis, on the basis of data someone else published, and he says, aha, let me go back to the lab and see if this adds up. Or let's go back to the computer and test the statistics of these relationships. So what we've seen in the last few years is that we used to package the data layer and the presentation layer on the server side, and UI was a thin client. Then we moved to this stage, and this stage is the one that allows you, for instance, for the case of TCGA, I started by downloading it, and now I can do things like this. TCGA scope. This is again from a paper. So I can look at the patients. This is the Karnofsky score here. So I could say only patients that are asymptomatic. What was their age, their survival. Can go straight to CBio. So we didn't talk about data comments. CBio. So all of these resources that NIH is now sponsoring under the cloud pilots, that's what they are doing. They're exposing data-intensive, some of them already analytical-intensive resources through APIs, such that you can manipulate them from the client side at no cost to you. So it's an academic exercise of finding the networks of relationships between these tools. And of course, you can also look directly at the question. And I believe you can go, or you could. Yes, you can. See? Oh, it's straight to the tissue. So we went from tissues. Let's see if I can segment these guys now. Doing it. There it is. You could say, oh, it's a horrible segmentation. Right? I need to do some cluster analysis on this thing. There it is. Cluster analysis. Then on the fly. Instead of trees, let's have this. Let's now segment the trees in different ways. The advantage of using the web as a computer, not just as a global data space, but as a global compute space, is that we are pushing code to where we want the code to be used. It's not that I refactored cluster analysis and went back to Smith and Sokolow's numerical taxonomy book and find out. No, that's not the important part. The important part is that the final product is a piece of code that is injected in whatever domain you want. So I didn't do the injection on the web page of Pittsburgh. I'll do it if someone asks me. It's running out of time. So this one was important. Data commons and fairness. So I have a slide there. I think it's kind of self-explanatory. Unlike in the previous generation of standards, so I come from the Semantic Web, we are very big on standards, and then we have to loosen up. The 1 hour lesson with CCD was a traumatic project for many of us. And actually for all of you, because it cost $350 million of taxpayers' money. But we learned a lot with CCD, and it's important to remember those lessons as we move now to data commons and fairness. So this idea of evolvable data structures and APIs drives very much fair and data commons. So I already showed you a little bit about this, because it's written everywhere. How is it taught? So this is the type of conferences that our students are now pushing us to adopt and offer to pay for. Because they basically say, no, I don't want to listen to your class, I want to go to a Smash conference. So they start by saying speakers are not allowed to have any slides, interactive live sessions. So the way of teaching transdisciplinary sciences, this is in the NSF reports about data science, is very different from other sciences. So they are not as scholastic. We got this one, let's see. And this is for those who don't believe in computer science, you may believe in Forbes. So this idea that data socialization is such a thing, there's nothing to do with the Communist Party. It's this socialization of generating data and consuming the analysis performed on it. And that's where data science is right now. Not just in politics and in shopping and all these other things, but also in healthcare, probably to an extent that won't be matched by these other environments. This was AMIA. We see people now that instead of taking paper, they take pictures, so we are forced to create data services that if you text this number right now, you get this piece of code running in the cloud, and scale depending how many of you are using the resource. So when we talk about web, we're not just talking about web browsers. We are talking about the whole ecosystem of Internet of Things, of SMS, all sorts of interactions we have now with this middle layer that separates the data from the analytic environment. And this was me showing code. It's a highly cited paper. This one is 300 and some citations. Don't bother, the code doesn't work. And I'm not going to recode it. So lots of people ask for it. This is another one. We publish pretty pictures, but we can't push our data to the picture. You can just see the PDF and hope, oh, I wish I had the algorithm so I could see how my patients look in the picture. So again, this has to go right. And you've seen the rest. Final slide. So I go back to Sparks. So this is an idea of what web computer could be like. It goes back to the ideas of truth again from a long time ago, where we just had the same application we saw before embedded in what's called literal programming. So the idea of communicating causality or association of any type requires us to bring the researcher or in general the consumer of the analytic solution to the table. And I'll stop here, otherwise we don't have any time for questions.
Right.
All right.
So, given it seems like there's been a lot of progress in microservices as well as pushing Java code, data resources, are there leading frameworks or tools that people who have large data resources now can include so that things like Amazon Silk are more generally available? What are those?
So Node now presently drives a lot of this. So if you have a workflow you want to run on the server side, so I'm talking about server-side code now. So if you specifically want to run it on the server side, Node is aggregating many of these libraries. So Node will use other languages like C, for instance, the OpenCV package from Jonas is very popular, everybody uses it. Now it's a Node package as well. So we're really not talking about pushing languages out of the execution table. It's just out of the development table. So we don't expect, maybe I'm exaggerating, I don't know, we don't expect OpenCV to keep growing as fast as the equivalent libraries which do exist that analyze the images directly in the browser. We don't. And once they do it in the browser, they also do it on the server side and the Node. So we start by co-opting other people's libraries like OpenCV within C++, and then we start enriching it with things that we can distribute both sans and server side. Now, your question points on the client side for the last piece of the diagram, which is that we started by spending a lot of time understanding the API. For instance, for me to traverse the 17 million patient data set of the Department of Health, I'm playing caching games. I'm caching on both sides. I'm understanding who did the Department of Health contract. It was a company called Socrates. So I understood all the cache that's it. I cached mine. So basically, they behave like my hard disk. But what we are seeing now is that as these backends become very popular, they have variations. For those of you writing Fire apps, the Fire of CERN and the Fire of Epic are not exactly the same. And actually, neither of them is exactly the Fire of Harvard, where the original Sharp Award created this thing. So what we see is that the community of people that on the client side creates an object, and it's this object's problem to map the different dialects of the same API. So once you have this object, you can, in a sense, wash your hand and says, I don't care. I'm going to assume that this works like silk. Because if it doesn't, someone else will produce one that does, and I just switch to the other one. So then we let the market, the ecosystem of computational agents, migrate to the point of delivery. Does this make sense?
Yeah. But from the perspective of
the developer, right?
The developer, are there leading, for example, I can submit map and reduce functions to a given enabled resource and have that run for me.
Yes.
Are there forerunners in that right now?
Yes, they are both in the commercial side and on the academic side. So the initiative at Argonne is still the reference on the academic side. The leading cloud providers, if you type serverless Google, serverless Amazon, serverless Azure, you find that they are exposing functions. Many students, they come to us already addicted to Heroku. Anyone? Yeah? Okay.
Yeah.
So they map it from their GitHub, and the thing is injected automatically. You don't even have to.
Right.
Every time you submit, it automatically maps, and the others do the same. So all the leading cloud companies do it. If you're doing something like TensorFlow, it makes sense to adopt a cloud provider that has specialized hardware. For instance, if you're using Google, they have TPUs. If you're using something else, maybe you want to use a cloud provider that has NVIDIA boards on the other side. But these calculations, I would say I make them because I have to have a CTO title next to the professor, and I have to worry about the bills at the end of the day. But I think for most consumers, you shouldn't worry about this because you see the price. The price is going to be smaller in the place that is better configured. So you have a clue where you're heading. All right. Time for lunch.
So I have a very practical question. In terms of the Center for Causal Discovery, where we're trying to both provide algorithmic software resources for analyzing data to obtain causal insights, and we're trying to prepare for the future so that this has hopefully a fairly long life, this software itself and how it evolves. What do you recommend that we do sort of practically at this point in terms of languages that we use, architectures that we use, all of the things that you touched on in your talk, in order to both serve now and be prepared for the future?
So I think you guys are very lucky in that regard because you have Jonathan that is advocating exactly these sorts of serverless cloud-based environments. I think the problem we are all trying to solve that we don't know exactly how to is how to change the culture of a group of people that are used to work together in a certain way by exchanging equations, by being the best computational statistician in the room, or someone that is really good at nonlinear regression, for instance. For instance, to give you an example with machine learning, this is one more familiar to me, I was basically put out of business when the libraries became good. So a lot of the things we've been doing, they evolved towards a state where the library is good enough that those who made a living out of creating them, they're out of business. So I think the first step in this culture change is to understand the needs of staying close to the edge of the technology. Technology used to be not a concern of scientists. That was for engineers. Engineers worry about technology, we worry about the science. But I get the feeling the two are now close enough that we have to rearrange the way we socialize science. For instance, I have a network project with a colleague in Germany. And the first thing we did was to create an environment where I can copy-paste a transition matrix, and I can have the network assembled. And then you will say, the thing we talked last night, it says, well, let me try my algorithms for the shortest path, for distribution of degree, and so on. And so now the algorithms are all building on top of this. And you always end up with a situation, which is what data commons is about, that you have a data structure where you are embedding the attributes of your workflow, just like data frames do in R, for example. So we don't have a data frame, as far as I know, for your domain. You could be the first one to create it. And once you do, others are more likely to adopt yours, taking as a link injected in their code, in their work environment, because there are no downloads anymore, no Dockers, nothing. It's just a straight code injection. And then they are more likely to build their algorithms on top of your core abstraction. The last thing about these sorts of issues is that I get the feeling that when there is no data, there is eventually nothing. Even if we have very good ideas, if there isn't a data that serves as a reference and a constituency that will consume the results of the analysis, we tend to go back into a CAD scenario. We just get pushed to a little corner and we are writing things others don't use. I know it's not an easy challenge to solve. More hackathons, I think, always helps. That's one thing I found. Hackathons are always a good thing to break the barriers, let people say what they think. As you mentioned last night, the students think we are teaching them, that they are teaching us. And that's so the hackathons. So now speaking to the students, if your professors invite you to a hackathon, do not say no. Because this is your chance to influence the way you're taught. It's not the scholastic model anymore. It's my direction.
Next time.